Cymatics is the study of visible sound and visible vibrations. By transmitting sound waves through any sort of medium, we are able to see different patterns emerging.
Humans perceive the different frequencies of the wavelengths with a vascular membrane, which width and thickness throughout its length vary, making it vibrate on different places depending on the frequency, as shown in the animation. The Rubens tube demonstration shown in the video gives a dramatic and visual representation of sound waves creating standing waves in a pipe. Sound waves consist of alternating regions of high and low pressure. But by igniting the gas in the tube and allowing it to escape out the holes in the top, we can see where the pressure is high and where it is low. So why do these patterns form? It has to do with constructive and deconstructive interference of the sound waves. What's happening is that sound is continuously traveling back and forth along the tube. Due to the fact that the waves reflect off each end, the sound is continually being produced by the speaker, so as sound traveling in one direction along the tube encounters sound traveling in the opposite direction, the waves interfere with each other. In places where two high-pressure regions overlap, we get constructive interference, and the wave amplitude increases. Where high pressure encounters low pressure, we get deconstructive interference, and the wave amplitude can drop to zero. If we generate sound at the right frequency for the length of the tube, we can generate a standing wave, where the location for deconstructive and constructive interference always occurs at the same place, forming a standing pattern. The distance between the standing wave peaks is the wavelength of the sound at that frequency. And this is how it looks with a song. Wave after wave, wave after wave, slowly. The frequency varies in the music, but we can perfectly see the change in amplitude when the volume goes up or down. For this project, we used a tone generator connected with an amplifier and a woofer that went from 20 Hz to 20,000 Hz of frequency. We went outside and connected a water hose to the woofer. This is a camera trick. If the speaker is vibrating at the same rate as the camera's frame rate, the water will be in the same position each time a frame is taken and will appear to freeze. The camera was filming at 24 frames per second and the woofer was hitting a frequency of 24 Hz. When we increased to 25 Hz, the water seemed to go down, and when we used 23 Hz, the water looked as if it was going up. At 24 Hz, it stayed still. At first it didn't work because the shutter speed wasn't the appropriate. It had to be 1/2000 in shutter speed. The speed of sound in falling water is about 1,500 meters per second. The frequency was 24 Hz. Therefore, the wavelength is 62.5 meters. The standing wave can be clearly seen when the water is a spiral. The nodes are non-moving spots in the wave and the antinodes are the parts with motion of the wave. The sound is visible by making the water create a geometric pattern in the shape of a helix spiral. This is a mixture of corn flour and water, and it's a well-known example of a non-Newtonian fluid. When on a speaker, the sound waves provide the force to solidify the fluid, but only at certain places due to the wave nature of sound. Constructive interference causes solidification and can cause the fluid to erupt into tentacle shapes, whereas destructive interference leaves the fluid in its liquid state. A strong enough speaker can bounce the entire mass of corn flour off its cone, but as soon as it leaves the surface, it will become a liquid again. A high pitch won't work with this experiment because even though there are more vibrations per second from the woofer, the force of the vibrations are less, meaning that we have to use a low frequency like 34 Hz in order to have this tentacle appearance.